towering spectacularly over West London. The biggest single-span arch in the world. Visible for 21 kilometres across the city.
Beneath this record-breaking arch is the most expensive sports arena ever built, Wembley Stadium.
But this extraordinary architectural feat owes much of its glory to some surprising engineering connections. A crossbow.
God, that's got some shove, hasn't it?
A rock climber's knot.
I remember I used to have arms.
A 19th century glider. A fake gold crown and Archimedes' most famous principle.
I'm not just walking on water, I am running.
And stealth aircraft.
How did all those make this spectacular stadium possible? When almost £1 billion is spent replacing a world-famous stadium, you'd expect to be impressed.
Underneath that vast arch hangs a giant 11-acre roof that covers 90,000 seats.
Each seat has perfect views of the immaculate turf. And no worries if you're caught short. There are 2,618 lavatories, more than any other stadium.
Impressive, but rebuilding the home of football pushed the architects and the engineers to their limits.
One of the biggest challenges was to make every one of the 90,000 seats feel like the best in the house. They had to be spacious, comfortable, sheltered, and each one with the perfect view of the pitch. And that meant no obstructions. Things like columns supporting the roof.
The solution involved building a massive arch that would hold up the roof from above, so no more columns. Norman Foster, one of the world's leading architects, wanted to build an arch that would stand out on London's skyline. But not just any arch. It was going to be the largest single-span roof structure ever built.
Not only had this never been tried before, but as this was the rebirth of an icon, the eyes of the world were on the aesthetics as well as the engineering.
At 133 metres tall, Wembley is the only stadium in the world to have beacons for low-flying aircraft. And with a 7.4-metre diameter, the arch is wide enough to drive a Eurostar train through.
But building the arch wasn't the only problem. Getting it up there was no walk in the park.
The engineers at Wembley faced a dilemma. They couldn't use traditional cranes to raise the arch. At 1,750 tons, the weight of 10 jumbo jets, it was just too heavy. The answer to their problem lay in a mountaineer's knot. And the first connection brings me to the bottom of a cliff.
Just stick it on a figure of 8.
Climbing instructor Chris Hurley takes me through the paces.
Okay, we need to attach it to 2 points.
Okay, that's okay.
You enjoying that?
No. This knot is going to be an essential part of whatever it is we're about to do.
Yes.
Is it going to be supporting any weight?
It's called a Prusik knot, invented in 1931 by Austrian mountaineer Dr. Karl Prusik.
Sit down again.
Yeah, please.
In theory, a couple of these knots are going to take me up this sheer cliff, with the ropes taking all the strain. Me just looking good in that hat.
Now, Chris, how do these knots actually work?
Okay, basically, you create a lot of friction on the rope. I've got one here, which I'll just put on and show you. Take the loop, put it around the outside of the rope. You then pull the rest of the loop on the inside of the larger loop that you've just created.
Yeah.
And then you do that again on the inside.
So does every climber know how to tie one of these?
Well, I should hope so.
Yeah.
Okay?
And the effect of that is a lot of rope from the support rope in contact with the other rope.
Yeah,
So
absolutely.
there's a lot of friction between them. So as soon as you put the load on, that's a lot of rope in contact with the rope. It's a lot of friction. It'll hold the load. It sort of locks itself, doesn't it?
It does. It just locks up on itself, yeah.
Friction stops me falling. But to heave myself up the cliff, I need 2 of these knots working together.
Tuck your foot in behind you a little bit.
Yes.
Now stand up on that nice and straight. It'll take a lot of the effort out
I'm
of it.
there again. Right. So that's the whole point of this system is it's got 2 anchor points.
Yes.
The lower one, the higher one.
Yes.
And at any given time, the load is supported by one of them.
Yes.
At this moment, it's the top one.
Yeah.
Slide the other one up to it.
Yes. And then you just, it's
And then
a
we do another
continuous
advance.
process. So you just basically repeat the process again and again.
Has anybody ever raced it?
Not with pressing knots, I shouldn't say.
Importantly, these knots provide a secure way to climb a free hanging rope.
This is the hard bit up here.
What? You mean the rest of it hasn't been? I can certainly see, as a system, it's just brilliantly clever in its simplicity. 2 points moving, advancing slowly up the rope. One thing you can't deny is even with just me on the end of it, it's a lot of work. Not the gripping, not the friction, that's easy.
Yeah.
But advancing, moving on each time.
One knot is always locked while the other one slides up. And this is the principle the engineers at Wembley would find crucial for lifting their arch. They had to make sure the arch wouldn't crash back to Earth during the lift. So they attached metal cables to the arch as it lay on its side. But they would need something stronger than string knots to pull it upright through 112 degrees.
Enter the engineering equivalent of the pressing knot, and a huge power source doing the work of my legs. They're called strand jacks, and it took 25 of them 4 weeks to raise the Wembley arch.
It was a mammoth lifting task requiring 130 kilometers of steel cable. All this cable ran through these stationary strand jacks. Inside the jacks, metal anchors work in pairs, just like the pressing knots. One is fixed whilst the other is moved by a piston. As the piston moves, the anchor grips the strand and pulls it through. Then the piston moves back with the anchor, while the fixed anchor grips the strand and takes the weight. The whole process repeats, slowly but surely. And this allowed engineers to raise the arch by 5 degrees a day until it was in position. The jacks that pulled the Wembley arch up didn't just have one strand, they had 38 each. The combined pulling force of all these jacks was nearly 12,000 tons. That's the equivalent of 6,000 4x4s all pulling at once. This massive feat of engineering was only possible because of a principle previously used in a climbing knot. But getting it up there was only half the story. There was still the roof to consider.
And that was the next big challenge. Just how do you connect a massive arch to an even bigger roof? For the answer, the engineers had to reach for the sky.
The architects at Wembley Stadium wanted the mighty arch to hold up as much of the 11 acres of roof as possible. If the engineers didn't get it right, the whole thing would collapse into the stadium below.
Not only did 7,000 tons of roof need supporting, the engineers needed to find a way to secure 1,750 tons of the arch itself, freestanding high above London.
Engineers needed the arch to hold up the roof, but then they had to stop the arch from buckling under the weight. So they turned to the first aviators for inspiration. Though the Wright brothers famously took their first powered aircraft into the skies over America in 1903, Wembley's connection with aviation goes back even further, nearly 100 years earlier, to an English inventor, Sir George Cayley, who was already testing model gliders. Cayley's pioneering designs, like this modern replica, would influence all future flying machines. And his glider would help the Wembley Arch hold up the roof.
Cayley was the first to really grasp aerodynamic techniques. He was confident he could get someone into the air safely. It was just getting them back to Earth safely that was the tricky bit. He realised that if he wanted someone to fly his glider, they needed to be able to land it safely, and to do that, he'd need strong, rolling undercarriage, and that's where the problems set in.
All Cayley had to work with were wheels made of wood. So to find out just what Cayley was up against, I've enlisted the help of James Bond stuntman Derek Lee and his bike.
What we have here is an experiment to try and demonstrate the problem facing Cayley. So we have a bicycle, but we've replaced the front wheel with one made of wood. Well, the point is that the problems with wooden wheels for Cayley for his glider were, first of all, that they were heavy. So to try and fly them, it's really, really heavy. I can feel that straight away, which is going to affect your flight. What I had said there and what I did say is flight. Because what we're standing on is the last piece of kit. This is a ramp. You're going to try and actually jump this bicycle.
I'm going to jump it. Not very far, but I'm going to try and jump it.
The idea is we'll see, first of all, if the weight ruins his chances of getting in the air, and secondly, and perhaps more importantly, what happens on landing. So when you land on that wooden wheel... OK, we really don't know. This hasn't been done as far as we know. I'll go over there. I think let's get ready. Let's do this.
Okay.
Yeah? You've done everything you need. The bike's ready.
Yeah, I'm sorted. I'm padded up.
Good luck, Derek.
Cheers.
Rather him than me. Here he comes. He's halfway here. He's going to make the ramp. He's going to make the ramp. Yeah, we can see quite clearly that a wooden wheel with spokes operating under compression is just not up to the job. Derek, however, are you all right, mate? You've ruined the wheel, look. That's utterly ruined.
I thought that might happen.
Yeah, it did, and it was the landing that did it. You managed, incredibly, to fly the wheel further than I thought you would, despite it being really very heavy, but then, on landing, it just blew itself apart. Cayley foresaw that. He wouldn't have done that, what you just did.
The wooden wheel shattered on impact. It just wasn't strong enough. Not great for a glider coming back to Earth.
That's where Cayley's other great invention came in. The wheel. Well, not the actual wheel, obviously, but in 1808 he introduced a revolutionary new type of wheel. It might look like just a bicycle wheel, but that's because Cayley's invention became the bicycle wheel as we know it today. Cayley's new idea revolutionized thinking at the time. Instead of using spokes under compression, he put his spokes under tension.
Equally tensioned spokes constantly pull the wheel together and give it strength. On impact, all the spokes act together to keep it in shape. And materials that are good at withstanding tension can also be light, like wire. So these new wheels were much easier to get off the ground and much less likely to break on impact, essential for landing gliders safely. Fast forward 2 centuries. BMX riders now rely on Cayley's invention to push their bikes to the limits. The light but strong wheel is a simple but blindingly clever invention. And there's one way to show just how it works. So BMX rider Dennis Wingham is lending me his bike.
The most important part of this wheel is the one thing you can't see. So it's not the rim, it's not the spokes themselves, it's actually the tension in the spokes. That's what's pulling the wheel together. So what I've done, obviously, is take that tension out of the spokes. So now the wheel isn't holding itself together the way it should, which means we can see how much difference and how important that tension is. Good luck. It may not work as well as it did, sorry. Yeah, I think that's kind of proved the point. Take the tension out of a tensioned wheel and it's got nothing to offer at all. It's no good to anyone. Well, especially not Dennis. I think he might be cross.
So tension is the crucial principle. Cayley successfully achieved the first manned glider flight in 1853. And the bicycle business has never looked back.
Tension spokes allowed the wheel to outperform anything you'd expect of any of the individual elements. They'd be too frail, too weak to do the job on their own. But working together like this, they're immensely strong. So for me, certainly, Cayley really is the man who reinvented the wheel. But what's this got to do with Wembley?
The Wembley Arch spans the entire width of the stadium. That's the length of 3 football pitches end to end. But that's not all. It has to hold up most of the 7,000 tons of roof. Engineers had to make sure the iconic arch would be strong enough to take the load.
Now imagine this arch as a giant wheel rim. And, yeah, you've guessed it, the wires coming out of it are giant spokes.
Like bike spokes on a wheel, tensioned cables are the key to making the arch work. And Alistair Lenchner was the engineer behind the design. We're being led right up onto the roof to see just how it works. Yep, onto a thin roof with nothing supporting it from below. Nothing at all.
How thick is this metal?
This is 1.2 millimeters thick aluminium.
1.2 mil.
Yes.
Could you use anything thinner? The roof flexes.
So here we are. This is a cable which, when you stood outside the stadium, looks like a little thread.
That's massive, isn't it?
It's a big cable, but it's actually part of the structure which supports the whole roof.
Well, the whole structure, actually, when you're down there, it looks delicate and fine, but up here now, we can finally get close to it. What's it doing? What's happening?
Yeah. This arch, it's not there just for decoration, though we think it looks great. It's holding the roof up.
These cables pull the roof up towards the arch. But that's not all.
But then we've got to make it stable, and these same cables hold the arch in its shape to stop it from buckling like that or like that.
So those cables really are working like the spokes on a wheel then, holding the thing in shape.
The arch and the cables work as a mutually supporting system. One without the other wouldn't work. It's the weight of the roof itself that tensions the cables and makes the arch stronger. 6 kilometers of these cables stop this enormous arch from failing catastrophically. And they mean that this 11-acre roof doesn't need any supporting columns.
Unobstructed views from every seat. Great for the spectators, and all thanks to Cayley's glider.
But this was the next problem. A big roof would be bad for the grass pitch. Wembley's roof provides 90,000 fans with seating that's sheltered from the rain. That's more than in any other stadium in the world. But what's good for the fans isn't always good for the game.
The focus of any football stadium, obviously, is the pitch, the grass. To grow quality grass, you need water, ventilation, and daylight. Lots of daylight. In an enclosed stadium, that's not easy to achieve.
For UEFA five-star status, Wembley needed to keep its famous natural turf in tip-top condition. So the designers kept the area above the pitch open to the sky. But grass needs as much direct sunlight as possible, and that means no shadows. The answer was to retract the roof on the south side. But the south roof consists of 7 giant panels, totaling over 3 acres. That's enough to cover St. Paul's Cathedral.
Engineering a sliding roof wouldn't be easy. There were 3 main problems: the weight of the roof itself, the effect of wind, and the need for precise positioning of each of the 7 sections of the roof every time it closed. So how'd you do that? The engineers turned to an invention that helped medieval archers.
This connection takes me back to the Middle Ages, when defending a castle was a full-time occupation, and archers on the battlements were the frontline force. Mastering the longbow took years of training. So warlords needed a bow that was easier to use, but just as powerful. They turned to the crossbow.
They could, I'm told, be fired after little training, and they could be kept cocked, which gave the archers longer to try and take aim with it. And it meant they could fire immediately if surprised. And at first, crossbow archers needed less upper body strength. Sounds like my kind of weapon.
But the early crossbow needed more power. Archery expert Steve Rouse trains Hollywood stars, and he's going to show me how a simple device made the crossbow a weapon to be reckoned with.
Steve, well, we're not making a salad, are we?
No.
So what are we doing?
We're here to see a timeline of crossbows, to see how the power develops.
First up, I'm trying the basic crossbow that, like me, needs a bit of help.
Hand
then
inside
what?
of the string,
Yeah.
then we draw it back into the nut.
This is
all
called
the
the
way
nut. That's quite difficult.
up onto your shoulder.
Right,
Now,
okay.
fingers away while I
Fingers away.
load.
Yes, that'd be a good idea.
Right, we're ready to go. So take good aim.
Okay, I'm gonna fire. I missed quite badly.
It wasn't just me. The strong wind made my bolt veer off course. To hit the melons, I need a way to get more power out of the crossbow. That means I need a new way to draw back my crossbow, just like the medieval archers.
So when we go up in power, we have to move to the next thing, which is a more powerful crossbow that you can't span by hand. I'd like you to try and draw that back, just using your physical strength.
Well,
To draw this, I need to pull the equivalent of 160 kilos in weight. That's like lifting more than 6 bags of cement at once.
clearly, I can't pull that by hand, no.
What you want is one of these.
A coffee grinder.
No, a cranoquin.
So this was a separate machine then?
Oh, yes. This is the first time where you're going to get a mechanical advantage using a cog and rail. So if you wind this handle... Now, you know how hard it was a minute
It was
ago?
impossible, yeah. But suddenly that's... Well, I can use one finger.
Exactly.
So that meant you could draw bows of immense strength, I bet. So what we've got in here as I turn this handle is it's turning a cog.
It's turning a cog that turns a larger cog that sits in here. So for the first time, you've now got this machine which enables you to store more energy within the crossbow. Yeah, give it some slack. There we go.
So when those were invented, all of a sudden you could have some almighty powerful crossbows
Some serious energy being stored there.
in there, ready for use whenever I
Yeah.
want to. Right, can I fire this one as well?
You can. It has a bit of a kick. So do you want a glove just to
Oh, yes.
go on this hand here?
I get kit. Excellent. I'm terrified of this thing once it's primed like this because it's so much energy stored in it. Okay, up.
Whenever you're ready.
Incoming. Go! That's got some shove, hasn't it? Can we have a look?
Yeah, I think it's buried in the next county, that one. Through and just disappeared. As the bows have become more powerful, we've got a different amount, but that one's gone.
So that we really have illustrated the different powers of the different bows, because there's this one barely in, this one just in,
Yeah.
that's, and the last one is just
It's gone.
This bow can shoot a bolt 100 metres further than the hand-drawn one. And it's all thanks to the Cranaquin, a cog and rail system that can draw back a great weight with ease.
It worked, an efficient way to use a cog and rail. But this system was only part of the inspiration for the way the engineers moved the 4 acres of Wembley's roof. If you look at the way this works, you turn the handle and it turns the cog, and that moves the rail back. That's what draws the bowstring back. What if the system worked the other way around, though? What if the rail stays still and the cog moves along it? This development in what is today known as a rack and pinion system was the next step in making Wembley's roof retract.
The rack and pinion system takes us back to 1812 and the early days of steam locomotion. British engineers wanted to draw heavier loads of coal, so their steam engines needed to have enough traction. Mine manager John Blenkinsop had an idea. He added a toothed rail to his tracks, and he fitted a cog to one of his engine's wheels. And it was a great success, allowing his engine to move 4 times more coal than earlier engines. And mountain railways like this one at Snowdon would later use the system to push passenger wagons up steep slopes.
So with Blenkinsop's railway and the brilliant medieval Cranaquin proving how effective rack and pinion can be, the engineers at Wembley decided to use a similar system to move the stadium's roof.
I want to see it up close, but that means climbing again, 52 metres above the pitch. The 4 acres of roof are currently open. So Henry Munro, Wembley's technical manager, guides me in between the stacked panels.
Everything here is massive.
This panel alone clocks in at 330 tons. That's the weight of 2 jumbo jets, and it runs the entire length of the pitch. Moving it is the job of the rack and pinion system. I'm here to see it in action.
This is the drive unit itself.
So this is a control panel.
That's correct.
I expected to do millions of buttons, but I suppose it can only do 2 things. Can we close it?
Yeah, just press the button.
What? I can do it.
You can do it.
You'll let me drive.
I'll let you drive this time.
Close roof, yeah?
Close
Just
roof.
press once, and I'm going to close the roof at Wembley Stadium. Is that a good thing? So this is where the cogs are doing their thing, driving along this toothed rail here.
And they're the main drive units here. There's 3 of them on this side, and there's 3 of them on the other side there, moving it.
And standing this close to it, I don't know, here it looks really, you can see the mechanics of it, you can see it working, but you don't get a sense of just the scale of it. Then you move back, and suddenly everything I can see is moving that way. It's massive, isn't it?
It takes 57 minutes for all 1,240 tons of the 7 panels to fully close or open.
It is staggering to think that something this enormous, I mean, it is mind-numbingly vast, can be tracked directly back to that Cranaquin. And the man decided to use a cog running along that rail to draw the bowstring back.
And the cog and rail keeps the roof in place to the millimetre.
So, thanks to medieval arches, mountain railways, cogs and rails, the 4 acres of steel shelter slide over the seats of Wembley with pinpoint accuracy every time. So that solved the problem of keeping 90,000 fans dry whilst getting as much light onto the grass as possible.
But keeping fans happy presented the engineers with another challenge. The acoustics.
To fans and players alike, the atmosphere of Old Wembley was incredible. Mainly thanks to the famous Wembley roar, caused by the fans' reverberating chorus.
The Wembley roar is caused by cheers bouncing off the flat surfaces inside the stadium. The designers of the new Wembley wanted to recreate this ambience, so that meant keeping Wembley's echoes. I'm on my way to investigate the effect at a rather larger flat surface. A cliff face.
Now, we all know what an echo is. It's just sound reflecting back off a surface. So, here is one. But it's the time taken between the original sound, the source, and the echo that's important.
Sound travels in a wave towards the cliff and then bounces back to me.
See, if that is more than 40 milliseconds between the original noise and the echo coming back, then the brain hears two distinct and separate sounds. But if it's less than 40 milliseconds, the brain just hears one sound. It assumes it's all the same thing. So, I hear exactly the same note back from this air horn. There it is, and the same with the gun. But those are just simple, single noises.
As lots of echoes bounce off multiple surfaces, they build up to create one big noise. And that's what makes the famous Wembley roar. But historically, Wembley is not just a football stadium, it's also a concert venue, and it's played host to some of the world's largest musical events. Most famously, Live Aid, which rocked Old Wembley in 1985.
But unfortunately for some of the music fans paying a premium to see their favourite act, parts of the old Wembley Stadium hit a bum note, acoustically, that is. Some areas in the old stadium became notorious as the echo became focused into hot zones of reverb, concentrated by the bowl shape of the stadium.
And this was the dilemma facing engineers of the new Wembley. Designers wanted to install 160 glass-fronted corporate boxes in a ring around the pitch. But like the walls of the old stadium, they would create echoey acoustics at concerts. I'm going to demonstrate the problem with light instead of sound, and by filling a barn with smoke and mirrors. Luckily, sound physicist David Trevor Jones is with me to help.
David.
Hello there, Richard.
I like what you've done in here, it's very nice, but what are we doing with it?
We're trying to see sound.
It's ambitious.
Lights.
I like your theatrical gesture, very nice. Okay, so that's
Splendid. There we go.
Hang on, this is light, we're talking about sound, David, I know that.
This is a beam of sound. And we've got the member of the audience who's paid a lot of money to be sitting there watching the band.
Does sound behave this way? Is this straight and fair, that it would come and bounce, just as this has been reflected off a mirror, it would be reflected off the window of the box?
Sound's not quite as focused. It's a bit more blurry than this, but shows us what happens in physics terms.
Yeah. I'm just assuming then that the football, which is our member of the crowd, sitting over there, is not only getting this version of it. They presume that if that light over there is the source, they're hearing it once straight into their ears, and then once again bounced off here.
That's absolutely right. Exactly. They're getting an echo that's coming from behind them. And so there's a hot zone in the audience where the people sitting in that critical area are getting this echo bounced back from the whole ring of the director's boxes, all reflecting down into this area.
Wow. And so straight away, anywhere in that area with just 7 on the go, let alone all of those windows, you can see how presumably they'd hear different echoes, different times. It's going to be just... They're all travelling different distances, and it's going to be a mess.
It's going to be the most horrible sound you ever heard. It's going to be a cacophony.
This is exactly what the Wembley designers wanted to avoid. The answer would take them back to stealth technology.
The engineers had a tough brief. Keep enough reverb to retain the famous Wembley roar, but get rid of those annoying hot zones. There is a solution, and the military use it to make things disappear.
The connection with the military goes back to the Cold War. In 1981, this top-secret aircraft flew for the first time. It's the F-117 Nighthawk, one of the early breed of stealth aircraft. The US Air Force designed this unusual plane to avoid detection by radar. Radar works by emitting and receiving electromagnetic waves.
And sound and radar waves generally behave in the same way. They bounce off surfaces at precisely the same angle as they hit them.
Normally, radar waves bounce back to give an echo, and this reveals where a plane is. But what if you change the angles of the plane's surface? Now the radar waves bounce off in different directions, and the original signal scatters. No coherent signal bounces back. And this is how the F-117 Nighthawk became invisible to radar receivers.
By applying the same laws of reflection to Wembley's hot zones, the designers could start to sort out their annoying echo.
Once again, we can see how this works with a beam of light.
David, a challenge. With this setup, you demonstrated the problem. Can you use just the same ingredients to demonstrate the solution?
Absolutely. It's very simple. We just slightly tilt the fronts of the boxes.
And as you do that, the light is moved off the hot zone.
That's right. And what we do is, with each of the director's box fronts, we angle each one just a little bit away from a coherent reflection.
OK, well, that works. I can see that works here now. But that's for an audience going there to watch a band. There were audiences, well, obviously, there to watch football matches, and they loved the roar, the echo, that big Wembley roar. That was part of the experience.
The Wembley roar. It's still there. All we've done is to spread it out a little bit. We've dispersed it. So far as the audience sitting around the ring of the stadium are concerned, they can still hear the reflected sound. They're still getting the Wembley roar.
So that's how you get rid of the hot zone and scatter the sound, but still keep that Wembley roar. You still keep the echoes. So that's how you can have your cake and eat it.
You can with an echo.
So the designers kept the echo. They just redirected it to prevent the hotspots.
As you can see, each window is angled slightly away from its neighbour, rather than facing directly onto the pitch. In fact, each pane is set at 5 degrees, and that creates this subtle zigzag effect. By breaking up the stadium curve with this zigzag, the engineers have ensured that the sound waves aren't reflected back into hotspots, but are now reflected off in all directions.
Now there are 21st century concert acoustics, but still the Wembley roar that football fans love.
But surprisingly, it wasn't the pitch or the acoustics at the top of the customer's list of improvements for the old stadium. It was the provision of something more basic.
When the half-time whistle blows, 90,000 fans have just 15 minutes to respond to the call of nature. So Wembley needs an awful lot of this.
Water. Wembley gets through hundreds of thousands of litres of the stuff every single match, much of it in a frenzy at half-time.
The fans need an awful lot of these. 2,618 to be precise, more than any other stadium in the world.
But having that many toilets flushing simultaneously creates a massive demand. So how do you store enough water for a mega flush without being, you know, caught short?
The answer lies down in the stadium's basement.
To keep up with demand, water had to be pumped around the building at massive speed. Faster, in fact, than it could be pumped into the building from the flow of mains. So there was no way supply could keep up with demand.
So the designers built 3 gigantic tanks. They can store 740,000 litres of water. That's enough for me to have a bath every night for 25 years. But the problem was keeping them full. I'm going to see the solution for myself. And it connects Wembley back to a principle first discovered over 2,000 years ago.
Inside this enormous tank, there is, well, an enormous ball cock. It's just like the ones you might have at home in your cistern, only a lot bigger. There are sophisticated monitoring systems in there, but even today, the most reliable means of making sure that when the water level drops, the system is automatically switched on is with a ball cock. And it works, well, in exactly the same way as the one in the system at home works. There is a water flow valve here, and controlling that, off it comes this ball. As the water level is down, it opens the valve and lets water flow in. As the water level then rises, so does the ball on the end, until eventually it shuts off the valve and stops the water flow. This bit on the end, the float, is critical. And it floats because the weight of water it displaces is more than it weighs itself. So it works according to a principle first discovered in the 3rd century BC by a bloke called Archimedes, who'd been faced with a bit of a knotty problem.
A king at the time wanted to know if his new crown was made of solid gold. Archimedes realized that the crown's volume held the answer. The crown should have the same volume as its own weight in solid gold. And the best way of finding that out? Dropping the crown in water. The crown turned out to be a fake because it had a greater volume than the gold. And I can show you how that works.
These are gym weights, and together they add up to almost exactly the same weight as my body. That is a bath full of water.
The story we all know about Archimedes involves him getting into his bath. As he got in, the water level rose. The water he was displacing was equal to his own volume. This was his eureka moment, and it works for anything, whether it's a person, a crown, some gold, or gym weights.
69 kilos of gym weights have displaced enough water to raise the level by about, well, 3 centimetres in that bath. If I were made of exactly the same stuff as the gym weights, I would displace the same amount of water and raise it by the same level. There's only one way to find out. I've always wanted to do this, so I shall. Boots off. Okay, all in the name of science, a quick bath. Displacing water, displacing more. Displacing quite a lot more. I've got to put my whole volume under the water to see how much I do displace. If it's more than it's already more than the gym weights. Just find out how much more.
It's all to do with my volume, not my weight.
Okay, so I raised it by more, so my volume is different, so I'm not made of gym weights. Obviously, in Archimedes' case, well, the legend has it, he then leapt out of the bath at this point and ran naked down the street, shouting, "Eureka!" I'm not doing that bit. But all of this has been leading us towards his great idea, his principles of buoyancy.
And those principles have given me an idea. If you increase the volume of something without adding too much weight, you can make it float like a ballcock. Theoretically, if I can increase my volume and not my weight, I should be able to turn myself into a human ballcock and walk on water. These could be the answer.
My football boots. They're made from polystyrene, which is, of course, very light. But they are, as you can see, really quite big. So, technically, I should float, according to Archimedes. Can I have my life jacket, please? Just not that I don't have every faith in Archimedes. I'm going to slip them on. Bearing in mind what's happening here, then, is my weight, my mass, not increasing very much, but my volume increasing by quite a lot on account of the size of my boots. Thank you, Martin. And straight away, if my foot were just on its own in the water, it would be way too dense. I'm floating, I think. Could I have one of my special poles for walking on water? Thank you. Yeah. All I need to do now is adopt a suitably striking manly pose. Ooh. Okay. Okay. Right. I'm not just walking on water, I am running. The man out boating. This is very pleasant.
I'm still floating, amazingly. And that's all down to Archimedes, whose principles also keep over 2,500 lavatories at Wembley in full flush.
Thanks to a rock climber's knot, a glider, crossbow, stealth technology, a crown that wasn't a crown, and some very clever thinking from Archimedes, I'm on my way to Wembley. When I say on my way to, I'm missing a bit, but my direction isn't that good yet.